Right, so far we've distinguished various kinds of representation and said that symbols, maps, and so on can be about things in different ways. And we developed some basic concepts in the first video, and we looked at one particular case in which we can use the word representation with a great deal of confidence because we know the neuroanatomical pathways involved as we map from the primary sensory cortices back to their receptor surfaces, the retina, the skin, and the basilar membrane. Now we're going to move on to a different sense in which the word representation is used in cognitive science when thinking about brains and cognition. And here we are on speculative ground. This use of the word representation is not at all as secure as the one we developed in the last video. So we're now going to be entering a discussion which is held almost exclusively within the computational theory of mind, in which it's assumed that the activity of the brain gives rise to consciousness and thought, so that in principle, your thoughts are understood to be in your brain, and they're understood to be about something in the world. That's probably very familiar, but it's useful to recognize that it is a theoretical hypothesis. It's not as I said, we're on shakier ground here. But one of the big mysteries of thought is that I can have a thought about Paris or the Caribbean, and Paris is not here and the Caribbean is not here. This ability of thoughts to be about something that's not there seems to be quite unique in the natural world. We don't find planets that are about something or chemicals which are about something. This has the fancy name of intentionality. And here's, for example, a thinking cat, and we're using all the cartoons we can because this is a cartoon vision of the mind. The thinking cat is thinking about a cheeseburger, and the cheeseburger is not there, so there must be something in this thinking cat's head that corresponds to the cheeseburger. And we want to know, what's that relationship of correspondence? Now, if we pursue this line of questioning, then we ought to be able to find some pattern of activity in the brain which corresponds in some sense, or is about that cheeseburger, is related to it. And so there must be a representation of the cheeseburger in some sense. And part of our job is to figure out what that means. So as we start to think along these lines, one thing to ask ourselves is, would a representation of a cheeseburger have to look like a cheeseburger? We saw examples of the use of a 5-pointed star in a circle, which looked nothing like Salt Lake City, and yet could be used in one context unproblematically. We saw other symbols which did include an element of resemblance, airplanes referring to airports, and fishing referring to implementing a no fishing ban. So that's a question we could open up. What other properties of a cheeseburger beyond looking like it might it have? Because if I think of a cheeseburger, I'm not just thinking of the yellow color and the green lettuce leaves, I'm thinking of the taste and maybe the cost and maybe its ability to satisfy me. What kind of properties of a cheeseburger would you expect to find in a representation of a cheeseburger if this were to be found in something like a brain? Now, this tradition, the computational theory of mind, is developed within a particular view of language and cognition that places a great value on the notion of a proposition, which we met in the reasoning topic last time. And so one way to think here, using the notion of the language of thought hypothesis of Jerry Fodor, is that thoughts are a bit like sentences. We met that. And then the cheeseburger, the representation of a cheeseburger, would be a bit like the word cheeseburger as it occurs in a sentence. So I've written 3 sentences here, and I've replaced the word cheeseburger by the picture of a cheeseburger to illustrate this notion. But of course, the question of whether the representation of a cheeseburger needs any properties of similarity with a cheeseburger still needs to be investigated. If we're thinking along the lines of Jerry Fodor, remember that words have a more or less arbitrary relationship to the thing that they're about. So here I'm going to take that symbol pi, which means one thing in the context of the Greek language, means something different in the context of mathematics. I'm going to put it to use here. in my little ecosystem saying, I want a pie, pies are tasty, yes, we have no pies. I subverted the symbol and made it my own. So this just demonstrates that there's no need for the symbol to physically resemble its referent. Now, this language of thought hypothesis is a very limited way of thinking about the richness of what we mean by thought. It's only ever going to even inform or approximate a tiny bit of what we want to unpack with. But this was pursued enthusiastically in the 1960s and 70s and 80s by cognitive scientists. And around the same time, others objected. And they said, this doesn't work for me. My thoughts are not obviously sentences, although I'm familiar with the notion of inner speech, but this reliance on sentence-like representations just seemed wrong to a lot of people. So here's a little experiment. I'm going to give you a task. Picture a hippopotamus. Okay, you've pictured a hippopotamus, right? There's my hippopotamus. Was your hippopotamus blue? You may or may not know the answer to that. It is possible that you pictured a hippopotamus and didn't pin yourself down with respect to its color. Once my hippopotamus appears and it's blue, the notion of a blue hippopotamus becomes conceivable. So if your imagining of the hippopotamus had just conjured up a word-like representation of hippopotamus, that wouldn't have any particular color at all. And yet you can perhaps tell me, no, my hippopotamus wasn't blue, even though I hadn't considered color. And this opens the door to consideration of another aspect of thought, which is our ability to picture things. Mental images, as it were. Now, mental images are the stuff we talk about. No one's ever seen one publicly. These are not objective. We're talking about something hidden that we can ask people about. So when we say a mental image is a picture, we have to be careful because we're still unsure what a mental image is, but we could, flesh out this story too. So if we give people mental image tasks and ask them to do things like picture a hippopotamus, one thing we can ask them, is there a spatial arrangement to a mental image? So was your hippopotamus facing right or left? You may have an answer to that. You may not have an answer to that. If you imagine or picture up a scene with lots of things in it, is it possible for one of them to block out the other, as it is in a visual arrangement? I asked you about the color of your hippopotamus, and your hippopotamus may or may not have had a color up to that point. So the question we could ask here is, are all the elements of the thing being pictured fully specified? Or an interesting thing to think about is, could you conjure up a mental image that surprises you? Could you conjure up something and then, as it were, look at it and go, ooh, hadn't thought of that. Maybe, maybe not. So one of the big principal debates that went on for tens of years, about 20 or 30 years, was between people in cognitive science who wanted to understand thought in terms of sentences or propositions, and people in cognitive science who were more interested in this imagistic aspect. And so we enter what's known as the great mental imagery debate. What's at stake here? Well, what's at stake here is a view of the mind in which representations are used, and the question is, are they more image-like or are they more language-like? Then we get the obvious question of whether these representations resemble the thing that they're about. So an image has the visual appearance of something, whereas a word doesn't. Then we can ask, are these then symbols, or do they have meaning because they function in a collection of other signs to which they're related? In what sense should we understand these as representations? And particularly between the 60s and the 80s, there was a great vogue in cognitive science for thinking exclusively along computational lines, in which case the brain as a computer was a big symbol manipulating machines. Now, symbols lend themselves to a language-like treatment. It's kind of harder to work with symbols when you're dealing with images. But mental images are, of course, entirely subjective. So how can we find out the properties of mental images? Well, there's some very neat and quite ingenious experiments done in the 70s. by Shepard and Metzler. And what they would do is they would show people pairs of shapes like this, and they would say, are these possibly representations of the same shape, or would they differ? And what do you have to do to answer this task? Well, you have to kind of look at one and then sort of mentally rotate it onto the other to see that they fit. Now, do these two? I think, yeah, I can mentally rotate one onto the other and they will fit. I hope you come up with the same conclusion, and I also hope I'm not wrong. Here's another pair, and again we can ask, if you rotated one, would it coincide with the other? Are they the same or are they not the same? If you've made your mind up on that, here's one more. The answer is yes here. Here's one more. You can have a go at mentally rotating this, and you'll find these do not map one onto the other. It's quite a difficult task, isn't it? And the amount of time that it takes you is precisely what the experimenters were looking at. Now, unsurprisingly, it takes you more time to produce a response if the answer is no than if the answer is yes. If the answer is yes, you do it in your mind and then you kind of go, I see it now. Good. Whereas if the answer is no, you do it in your mind and you're not sure you've done it right, so it takes a bit longer. And what they looked at was how the time taken to respond depended on the amount to which these things would have to be rotated in actual space. And here's the results. Now on this plot there's two lines. The top blue line comes from trials where the answer was no, and the lower line comes from trials where the answer was yes. That is, one did map onto the other. We've discussed that difference. On the bottom, the x-axis, you see the amount to which you would have had to rotate these, in this case on a plane, to map one onto the other. So the important numbers here go from 0 to 180 degrees. After that, we're going back and approaching back to our original orientation. And the response time is the y-axis. And what you can clearly see is that the degree of rotation necessary to answer the question influences the amount of time taken to respond. So what this told us was that the geometric form of the stimuli used mattered. The amount of time that subjects needed depended directly on the amount that the shapes would have to be rotated in the three-dimensional world. Geometry really matters. And that means that in this instance, at least, we have a strong argument for a spatial or pictorial element to mental images, which cannot be accounted for in a merely language-like model. So that's a rather technical debate, but it went on for at least 30 years. Shades of it are still to be found in cognitive science, and it introduces you to a flavor of some more questions that arise as we open up this theme of representation.